Hi guys and welcome to my channel. Today I am bringing you a very special video because I am mixing two of my passions, of my favorite things in the entire world, Marvel and science. Let's explain the science behind the quantum realm. First of all, I want to tell you that I am a chemistry major, so I have taken a class on quantum mechanics and I am currently taking another one on quantum chemistry. First of all, I wanted to tell you the difference between quantum mechanics, quantum physics, quantum chemistry. What is all of this? Well, I think quantum mechanics is the general name for this discipline. If then we apply it more to chemistry, we have quantum chemistry, which deals more with atoms and molecules, and then with quantum physics, which deals more with particles. So last semester I had more of a general quantum mechanics, and this semester I am taking a class on quantum mechanics applied to molecules. So we're focusing on spectroscopy, which is something that is very relevant in chemistry because we use it for everything. Spectroscopic methods are extremely useful for a whole range of different things. So yeah, the first thing that I want to tell you about the quantum realm in mainly Ant-Man, but it will be probably more relevant in Avengers 4 and Captain Marvel and all of that. What I want to say is that don't believe everything that they tell you. This is obviously science fiction, not science. Yes, it can be based on actual phenomena that take place in the real world, but it is not true. Don't believe everything that they tell you. Well, don't believe anything that they tell you because it is real things applied to fiction, so science fiction. It can be created or presented to be believable, but it is actually not, so please don't believe all that they say. The first thing is that there is not such a thing as a quantum realm. It is just not true. Sorry if you thought it was going to be possible to reach there, but it is not. The main thing people criticize about the movie, and it is completely true, is that they include the term quantum before every single word, so they seem more sophisticated or more believable, but in real life, the word quantum doesn't appear as often as you think. In my whole university degree, the word quantum only appears like 3 times. I know. Obviously, in the term quantum mechanics, it also appears in the fluorescence quantum yield, which is something we studied in analytical chemistry when we were applying fluorescence to measure concentrations and all of that. And also the term quantum allowed, which is something we use because in classical physics, some phenomena are not allowed, they are forbidden, but if they are quantum allowed, it means that by quantum processes they can take place, so we use the term quantum allowed to refer to those processes. In this video, I'm not going to particularly dive into all the things that are said about the quantum realm, but I'm going to give you a basis about quantum theory, about quantum mechanics. So let's start. One of the major fails that I think people have is that they think that the laws of classical physics are wrong, but they are actually not. Quantum theory can explain absolutely everything from a tiny particle to a huge truck that is moving in a road or a train or something like that. It can explain everything. But there is a point that if your mass is big enough, you can take certain approximations, and if you make those approximations, you arrive to the classical equations. But of course, those approximations can't be applied to tiny particles because their mass is smaller, so you cannot apply those approximations. But actually, the classical physics equations and theories are an approximation of the quantum theory. Now I want to refer to a phenomena called quantum entanglement because some of the things in the film are explained by this phenomena, and what I want to say is that I have not properly studied it because it is more of a physical phenomena that I suppose physicists study, so I have not touched that in my studies, so I'm not going to be referring to that to see if it is believable or not, if it would be possible or not. And this is another example of a word that has quantum before it, and it is a proper and correct term. But there are very few words that are quantum something, and in the film there are a lot of them, a lot. So now let's dive into the basics of quantum mechanics. The thing here is that now what we are measuring is probabilities. We cannot know the certain value of something. We only know the probability, the likelihood of that phenomena to happen. We can also calculate the mean value and all of these things, but we cannot know the certain value of something. We can calculate, for example, the probability of an electron to be at a certain region at a certain time, but we cannot assure that it is going to be there. It is only a probability of the electron being there. And of course, you may think that electrons are moving around the nucleus, but in quantum mechanics, those electrons have no trajectory and they can be at two places at the same time. And this is the basis of the double slit experiment. This is a very complex issue. You can check some videos on YouTube because they are very interesting, but it is a very complicated process. Basically, we have a wall with two slits, and if we make an electron go towards the wall, we cannot know which slit it goes through. And we can say that it goes through both of them or through none of them at the same time. And you might say, wow, how that can be? Well, go ahead and watch some videos because they're going to make a better job than me at explaining it, because this is a thing you have to see with some pictures and drawings, and I don't know how to make animations, so I'm not going to attempt at explaining this, but it is a very, very, very interesting phenomenon that takes place in the real world. And I was talking about probabilities. Have you ever seen the drawing of an orbital? Well, here you have, for example, a picture, and orbitals are basically the area of space where electrons have a very big probability of being. These shapes are the representation of the functions of where the electrons are more likely to be, but we don't know if they are there or not. It is very probable that they are, but they might not be there. Another very interesting thing happens here in quantum mechanics with light. For example, well, with every particle, but let's take light. People didn't know if light was a particle or if it was a wave. People in the past made a lot of experiments trying to prove that it was one thing or the other, and with some experiments we can prove that light is a wave, and with other ones we can prove that light is a particle. So how can that be? Well, because it is both. This is called the wave-particle duality. It basically is that every particle has an associated wave, and that waves and particle are actually the same thing. So if you have a wave, you have a particle. If you have a particle, you have a wave. The main scientist that was responsible for this principle was de Broglie, and he's actually the scientist responsible for the equation that relates the momentum of the particle with the wavelength of the wave. And last but not least, to finish this video, I want to tell you a very interesting thing that is related to another scientist, and it is obviously Albert Einstein. No one can do a science video without mentioning him because he was a huge deal. He's responsible for science that is in different fields, and he is very important in quantum chemistry as well. If I asked you what is Einstein's biggest discovery, what do you think it is? Well, I'm sure you would answer relativity, the theory of relativity, both special relativity and general relativity. But let me tell you something. Einstein won the Nobel Prize. Do you know what it was for? It was not because of the theory of relativity. It is because he was able to explain a very important phenomenon in quantum mechanics, which is called photoelectric effect. This basically explains why if you irradiate light to a metal, the metal can eject some electrons. This phenomena cannot be explained with classical physics. Einstein was the one that was able to explain why, and he used Planck's theory of quantization of energy to explain this. These two theories are the pillars of quantum mechanics. They are the experiments that started quantum mechanics as a discipline and why it evolved so quickly. Planck and Einstein, which were extremely important figures in the development of quantum theory. That was all for today's video. I hope you didn't get very bored with this quantum theory lecture, but I think I made it as light as possible. But it might be a little bit boring if you are not interested in these things. But yeah, if you like this video, give it a huge thumbs up. Don't forget to subscribe and hit the notification bell so you don't miss any of my videos. Thank you so much for watching, and I will see you on my next video. Goodbye.